My name is Neri Ruiz, and I'm a recent graduate from University of Bridgeport.
My name is Brian Tavera, and I'm a current graduate student at the University of Bridgeport. And our research topic that we'll be presenting today would be intrusion detection system and the use of neural networks packet classification. Just a simple overview of what we will be talking about today in our presentation. We'll give you a short introduction, some related works that help us guide us with our choice in our research, the background regarding our research topic, the methodology that pertains to our topic, the implementation approach that we chose, followed by the results for that implementation, and we will conclude with a conclusion. So for the introduction, a DDoS attack is best known to be a malicious attempt to disrupt normal traffic or a targeted server, or basically when a network is too overwhelmed and flooded with network traffic. Several neural networks were trained in order to attack several data sets, which basically had different types of intrusion attack. Evaluated the packet classification accuracy, and we also compare the performance of these different neural networks. And for related works, machine learning and deep learning algorithms are mitigation techniques highly used for detection of intrusion attacks. For the research done for a reference one, or in other words, the title of the paper was called "A Practical Lightweight Deep Learning Solution for DDoS Attack Detection," and basically this paper produced a reduced convolutional neural network, which ended up saving computational resources and able to run these resources on constrained devices in order to detect these DDoS attacks.
Researchers in two DDoS detection approach, combining LSTM and Bayes, explore the method of using long short-term memory and Bayes algorithm to detect DDoS attack. Their method was to combine the LSTM to pre-classify the data and then passing that pre-classified data to a Bayes algorithm to reclassify the data. An author of three, DDoS attack detection using artificial neural network, used a simple neural network to detect DDoS attack. In their research, they examined the use of different backpropagation algorithms and explored their impacts on classification and performance. The background of neural networks. Artificial neural network is a mathematical model that mimics the brain's functions to weigh out the importance of certain features. This basically gives the ability to distinguish small differences in between very similar data. To understand this, we need to look into a single neuron. A single neuron will receive a data set, and each point of that data set will be applied to a weight. After all the weights are applied, the neuron will sum up these products and add it to a learned bias. Then this sum will be applied to an activation function. This activation function can be interpreted as a type of gate function that will pass either a high value or low value to the next neuron. When you add more neurons linked together, it becomes a neural network, which each neuron will interact with each other and finally giving an output of a classification answer. When linking single neurons, they all become a neural network. This interaction of single neurons becomes a very powerful classifier.
For the background on DDoS and IDS, IDS is just it's just an acronym that stands for Intrusion Detection System. And it is a device or software application that monitors a network for malicious activity. There are several types of DDoS attacks in which pertain to volume-based, protocol, and application layer attacks. Slow loris is another type of attack. It's basically what we primarily focused on our research. And slow loris is a type of denial of service attack, which allows a single machine to take down another machine's web server. So in other words, slow loaders basically keeps many connections open and holds them as long as possible in order to overwhelm the host server. Leading into the methodology, the main problem that basically needs to be addressed is how DDoS attacks can be minimized or at least be detected in someone's system. And the goal of an efficient intrusion detection system is to be able to detect patterns of the attack simply by analyzing the incoming network traffic behavior. And we believe that the best approach of detecting this occurrence should be through the use of recurrent neural networks.
Data preprocessing is an important topic when training any machine learning algorithm. In our research, we explored 3 ways of padding raw packets, and the type of padding is an important factor when training. The dataset that we used in this project, we used IDS 2018. This dataset consists of 400 plus gigabytes of raw PCAPs files. This is a good dataset since it simulates a good number of hosts and victims, and also simulates a large collection of different types of intrusive attacks. This dataset also was organized by host IP, date, and time. And what that means is that the dataset is broken into time sections where the attack is happening.
For the implementation, we're going to talk about the hardware and software aspects of our research. So for software, the main programming language that we use was Python, primarily version 3.6. We use CUDA Toolkit, a parallel computing platform and application program interface model that's created by NVIDIA. We use a specific library called TensorFlow, and it's basically known as an end-to-end open source platform for machine learning. Another open source library that we use was Kira's API, which provides a Python interface for artificial neural networks, followed by scikit-learn and NumPy library.
In terms of hardware that we used 2 systems. One with the i7 6700K and a Xeon 5 2620. This allows us to run multiple training sessions without interfering with each other. To accelerate training, we use 2 GPUs, specifically NVIDIA GTX 1080 and the GTX 1050 Ti. In our implementation of data processing, we came across 3 methods of processing our data. And here we have 3 images, and these images represent the data within the packet. Each pixel represents a byte from the packet. Now we came to this problem since our neural network model has a fixed input size. To resolve this issue, for cases of packet are smaller than the input size, we came to these methods of padding the packet. So the first method is double-sided zero padding. This method is basically adding zeros to the beginning of the packet and the end of the packet until it reaches the correct size. The second method is just zero padding. This is really straightforward, and it just adds zeros to the end of the packet. And then lastly, we have a repetitive padding, which repeats the data in the packet over until it reaches the correct size. This is our code for building a simple neural network. The first layer that we created using Keras, we created a input layer with an input shape of 1000 by 1. Then we added a Gaussian noise layer. This layer was meant to mitigate some overfitting that we were experiencing before. Added 3 hidden layers. The first hidden layer has 1000 neurons. Second hidden layer has 800 neurons. And the last hidden layer has 100. And the final layer, the output layer, has 3 outputs. The output signifies as normal traffic, DDoS attack, and other attack. The optimizers that we use is Atom, and for our loss function, we use cross entropy. Convolutional neural network, we basically try to keep it similar to our simple neural network. Our input layer, we used a input shape of 50 by 20, which matches the same number of inputs as the normal neural network. We have also a Gaussian noise layer for the purpose of mitigating overfitting, and we have two convolutional layers. Both layers have 3 filters with a kernel size of 5 by 5. And each convolutional layer also has a max pool layer after each convolutional layer. After these convolutional layers, we have a flattening layer, and then a dense hidden layer with only 100 neurons. And then the last layer is our final output layer with the 3 outputs. The optimizers that we used were the same as our simple neural network, Atom, and we used the same loss function, the cross entropy.
For validation, we represented our data using a confusion matrix. Confusion matrix is basically a table that is often used to describe the performance of a classification model or classifier on a set of test data for which the true values are already known. For example, we have the diagram on the right, which I could explain a little bit better. You'll have the actual values, or in other words, the expected values, what we already know what the data concludes, versus predicted values, or the output from the classifier. So using an example, for example, if in the data we have an expected attack, for example, let's say brute force, we know there's a brute force attack happening during this set of time. Uh, Based off our classifier, the output of the classifier also gave us that there was an attack. We will consider that a true positive. Whereas if in the data set, let's say there was no attack for brute force during that set interval time, and the classifier gave us a positive or expected output saying that there was an attack, we will consider that a false positive. And same thing pertains when there was no attack on either side, vice versa. Just a few other components that pertain to the confusion matrix. So, for example, precision. Precision is a component, and it is defined as the number of true positives divided by the sum of true positives and false positives. And below is the formula for a better representation. For recall, recall is basically the ability to find all relevant instances in a data set, or it's better defined by the number of true positives divided by the sum of true positives and false negatives, as you can see as the formula below. And lastly, another component that's made up for the confusion matrix is F1 score, and that is the measure of a model's accuracy on a data set, and it is a way of combining the precision's recall and the mean of the model's precision and recall. And there's the formula below. So followed by our results using the zero padding approach. For zero padding neural network, we received a total accuracy of 90.44%. The confusion matrix gave us the output for normal traffic type with a 0.98 precision, 0.92 recall, and a 0.95 F1 score. Whereas for the attack, there was a 0.27 chance that there was an attack. There was a 0.68 recall and 0.39 F1 score overall. And for convolutional neural network, we almost received just similar results, almost right about the same total accuracy and percentage. So for the convolutional neural network total accuracy, we received an 89.79%. And as we could quickly see over here, For the confusion matrix, the outputs that we received, the results for normal type traffic, we received 1.00 precision, 0.90 recall, 0.95 F1 score. And for attacks, slightly less than what we received in zero padding approach for the neural networks. For the results for the repetitive padding, so just summarizing again the differences between the two. So with repetitive padding, we're looping or feeding the data again and again in order to receive more precise results. So for the repetitive padding for the neural network classifier, as you can see, the precision was slightly less. It was 0.88 for the normal flow traffic, 0.92 recall, 0.90 F1 score. As for the attacks, we received almost about 50% precision with 0.42, recall 0.31, and F1 score 0.35. And the total accuracy on this aspect was 82.98, which was quite surprising. For the repetitive pattern for the convolutional neural network, the results were also similar. So with the percentage of having a total accuracy of 87.48%. And on the next slide, we will compare the two side by side and further explain into more detail.
For our final discussion, we place both results side by side. Viewing zero padding, we see that the total accuracy for both neural networks have a high accuracy comparing to repetitive padding. But however, repetitive padding has a higher precision when detecting attack scenarios, which proves that we're using repetitive padding as the preferred choice of padding actually improves the overall performance of the neural network. To conclude, we collected the results from our confusion matrix, calculated the precision, recall, and F1 score to analyze our classifier's performance. The results that we collected, we can state that the simple neural network has the highest performance in classifying this type of data, with reaching an accuracy of 82% total accuracy and a precision of 42% using the repetitive padding to detect malicious packets.
So from our research, we came to a conclusion that the simple and convolutional neural networks trained with repetitive padding had a lower overall accuracy compared to the classifiers that were trained with zero padding. Followed by that the repetitive padding improved the classifier's precision performance for classifying attack scenarios in contrast to zero padding. Based off our conclusion, in order to further evolve our project and for further research, we believe that a data mining approach would be an ideal way to pre-process data.
By what we mean by data mining approach is to collect the overall features of each connection, and with this features that we collect, we use these features to train the neural network, and this should improve the classification network performance over classifying from raw packets. Thank you. This concludes our presentation of our current research.
Thank you for taking the time to watch our presentation. Here are our emails, followed by our LinkedIn, and you can reach out to us with any questions or any comments. Thank you so much.